I'd say you care the most among the professors because I like to care about teaching.
Yes.
Well, the issue
Okay, good morning everyone. Good morning. Alright, before I begin class, a couple of quick words on homeworks. Your first homework is up. It's kind of a simple one, okay? It's not much sweating there. What I will be doing in the future homeworks is I will be uploading the problems as a PDF. You'll be working it out using Notability or paper, whatever medium you choose, and then you'll upload it as a single PDF file. Okay? So this is the most efficient transfer of information between the two of us. And then once the homework has been submitted by you, I'll have the homework solutions posted. Okay, so that will be my work that you'll be seeing. And a word of caution for the second homework. I'm going to be posting it on Sunday night, but as you know, Monday is a holiday, which means that by the time we get to solving problems, it will be Wednesday. So you will be able to start your homework assignment after Wednesday's lecture. That is in realistic terms in solving the problem. But you are welcome to give it a crack based on whatever we have done in today's lecture. Okay, the equations that we see today is what you'll be seeing used in your homework assignment. And in future homeworks, it is highly likely that the material of the current week will be manifested in the homework problems. When that happens, I'll let you know. I'll say in the homework problem itself that, okay, hey, this is a topic that we may perhaps cover on Wednesday, and I'll make sure that I'm not going to ask you something that is too tedious on the current week's topic, just so that we are all on the same page. Alright, are there any questions or any issues that you want to resolve? Any bones to pick with before we start lecture today? During lecture, please, I request you to be on top of things. If you want to talk amongst yourselves, please go outside and do it. During lecture, we talk. I talk, you listen. You talk, I hear. Okay? Thank you. Okay, so we looked at two modes of heat transfer, conduction and convection. Conduction is energetic interactions between molecules. There is no bulk motion here. And the law, the phenomenological law that allows us to study conduction heat transfer is due to Fourier, the Fourier law. I will not be repeating the equations, we already saw it last time. Then we looked at convection heat transfer as well. This is transfer of energy between a surface and a fluid in the presence of bulk motion. So there is bulk motion permitted here. And the law that allows us to understand convection heat transfer is from Newton's law of cooling. And I'll write that equation. Q double prime is heat flux. Convection is H times T surface minus T infinity, assuming that Ts is greater than T infinity. Okay, H is the heat transfer coefficient. The whole aim of convection heat transfer is to come up with ways of obtaining this character H. Okay, and we will spend a good amount of time doing that. In convection heat transfer itself, you have two modes of convection: natural convection or free convection, and forced convection. Okay, so convection, forced convection, and then natural convection. Sometimes natural convection is called as free convection. Okay? Forced convection, the idea is very simple. I use an external agent to cause bulk motion. So I take a huge blower, blow wind past the plate. That's an example of forced convection. So external agent causes bulk motion. The majority of your time will be spent on forced convection. Okay? Natural convection or free convection is a much more trickier beast in a sense that there is no external agent. And so how is bulk motion caused then? Right? That's a question to answer. Very peripherally, not going into the depth of natural convection, here is what happens. Let's say that I have a surface, okay, Ts, and there is fluid on top of this surface. Okay, so there is fluid, T infinity. There is no external fan that is blowing this fluid past the plate and so on. So there are no external agents. If I assume that the surface is hotter than the fluid temperature, then what happens is the following. Because of the no-slip temperature condition, essentially it means that the bottommost layer of the fluid molecules will have the same temperature as the hot surface. They become lightheaded. Their density reduces because of the increase in the temperature. Because they are light, they will start swimming to the top, which means that they will dislodge the heavier particles which are sitting at the top. They'll be coming into the bottom. They will get in turn lighted up. Their density will become lesser. They'll keep going up, and this will keep on going and causing a natural convection pattern. Yes, so there is a natural flow that is happening, because of the intrinsic nature of the buoyancy forces. The buoyancy-induced forces due to a temperature gradient. Okay, so this is a buoyancy-driven flow due to temperature variations which reduce the density or increase the density and so on and so forth. So you have the bulk motion caused due to that. For the most part, we may very badly touch upon natural convection, but we will spend a good amount of time on forced convection. Okay? A fundamental difference, at least quantitative difference between natural and forced convection is in the value of the heat transfer coefficient. If you have forced convection, the value of H is high. If you have natural convection, the value of H is low. Okay, so H I'll write it somewhere here. Typically low for natural convection. What is H? H is the convective heat transfer coefficient. It's a function of so many variables, and it's our whole aim to find this quantity for many different types of problems. For the most part, it is empirical, experimentally determined. Alright, so that's it for convection. For the time being, okay, we're going to go into the deep details of it, the murky depths at some point in time later. We're going to look at a very interesting mode of heat transfer today, radiation heat transfer. This is the third mode of heat transfer. And once again, I tell you that, okay, the aim of the first few lectures is to introduce you to these different modes without going into the depths or the physics of it yet. We will spend a good amount of time doing the physics of radiation heat transfer. It is probably the most obtuse form of heat transfer because it involves a lot of geometrical considerations. So when I get to radiation heat transfer, I will probably not use the chalkboard, but I will be using my iPad to show you figures and then write on notability as I teach radiation heat transfer. It's a much better way of drawing the figures. Conduction is fairly straightforward to draw the figures and so on. Okay? Okay. So what is radiation heat transfer? You take any body, human body, whatever it is, any body at a temperature greater than 0 Kelvin, which is the absolute low temperature that you can get on a physical body. So any body at a temperature greater than 0 Kelvin will have a certain amount of internal energy. And as a consequence of this internal energy, the molecules within the body will start agitating. And this agitation results in energy that is emitted by the body in the form of electromagnetic radiation. And this is due to James Clerk Maxwell. Okay, so 1860s, 1864 is when electromagnetic theory was proposed by James Maxwell, and we owe it to him to understand radiation. Okay, so here is the basic idea. So any body greater than 0 Kelvin will emit energy in the form of electromagnetic waves due to molecular agitations within its body. Okay, so this is due to molecular agitations. That is, the molecules are vibrating, they're oscillating, they're disturbing the neighboring molecules, things are going on within the body itself. And as a consequence of that, there is a certain amount of energy emitted. The medium that this energy is transmitted is electromagnetic waves, which means that this is going to be transmitted at different wavelengths. And so you have the electromagnetic spectrum. You have radio waves, you have infrared waves, ultraviolet waves, and so on and so forth. Different wavelengths for these different portions of the spectrum. We are not interested in the full spectrum. We are interested in a small portion of the electromagnetic spectrum where energy is emitted in the form of heat and light. And we call that as thermal radiation. Okay? So our interest is on a small band of the electromagnetic spectrum. EM, electromagnetic spectrum, where energy is emitted as heat and light. and this is called as thermal radiation. Right. So this is the very peripheral physics of it. What I want to do is I want to introduce some equations that will enable us to solve problems for the time being, placeholders, and then we will dig into the physics of these things. Okay? So I'm going to consider a surface. At a temperature Ts, this is greater than 0 Kelvin. And 0 Kelvin, K capital. What's it going to do? It is going to emit radiant energy. The emitted energy, I'm going to write it in the form of a flux, which means this is energy transmitted per unit area. Okay? So this I'm going to call as capital E, and I'm going to start labeling things now. So E is called the emitted radiant flux. So this is in watts per meter square, or sometimes just called as emitted flux. Okay. Now we are going to introduce this notion of what is called as an ideal emitter. Ideal emitter of radiation. The sun is a classical example of an ideal emitter. An ideal emitter is defined in the following manner. No body can emit as much radiant flux as an ideal emitter. So no body emits as much radiant flux as the ideal emitter. And we'll spend a amount of time talking about the laws that enable us to classify certain surfaces as ideal emitters, certain surfaces as real surfaces or real emitters. The radiant flux that is emitted by an ideal emitter, and this is also pejoratively called as a black body. I don't like to use that term. I'm going to call this as an ideal emitter. Okay? So you'll see this defined in a certain way in your textbook. We're going to stick to the ideal emitter, or I'm going to define an ideal body in a few minutes. So E suffix B is the radiant flux emitted by an ideal emitter. Emitted by an ideal emitter, and the amount of this flux is given by what is called as the Boltzmann Law. So EB sigma T to the power 4. This is the Boltzmann Law. Joseph Stephan, Ludwig Boltzmann, seminal figures in the field of mechanics, heat transfer, quantum physics, quantum mechanics, and so on. Okay. Sigma is a Boltzmann constant. My shorthand notation is SB. So sigma has the following value, so an experimentally determined value, but it's consistently the same for all kinds of surfaces which are ideal emitters. 5.67, 10 to the power minus 8 units. This is in watts per meter square. When you talk about radiation, the temperature is always in Kelvin. If it is in degrees, it's garbage. The units are watts per meter square, Kelvin to the power 4, so T is always temperatures are in Kelvin only. So this is the characteristic of an ideal emitter. So most of the times we will have a real surface. This is an example of a real surface. A real surface will emit a fraction of the emitted flux of an ideal emitter. Okay, so E, which is the radiant flux emitted by the real surface, is a fraction of the total radiant flux from an ideal emitter. This fractional quantity is called as epsilon, which is called the emissivity of the surface. Epsilon is a quantity between 0 and 1. This is for a real surface. E suffix v is sigma t to the power 4, so you can substitute that and obtain the value of E for a real surface. If your surface is very highly polished, emissivity is low. If your surface is rough, emissivity is high. And we'll see why this is the case. And emissivity is dependent on the directionality, depends on the geometry of the surface, depends upon the surface finish, and depending on how the surface finish of the surface is, certain regions of the surface will emit energy in different wavelengths, and so epsilon is going to be a function of the wavelength as well. So it's a directional quantity, it's a spectral quantity. Spectral meaning it has something to do with wavelength. Okay? Alright, so this is what we have so far, and I'm going to erase this panel here, continue. Now what's going to happen is that if I have a surface, if I am a surface, I not only emit radiation, but I also receive radiation from all of you, good energy and bad energy, right? So which means that there is a certain amount of radiant flux that is incident on the surface. And this is called as irradiation. Okay, so I'm going to call it as G. So G is irradiation. This is the net radiant flux incident on the surface. And this G is also in units of watts per meter square. So so what's going to happen is the following. Okay, there is somebody throwing in energy at me. I'm going to do three things. I'm going to take some of that energy and transmit it to somebody else. I'm going to take some of that energy, absorb it and become more energetic. And I might also do the following. I might take some energy and reflect it back. So the total radiant flux is split into three quantities. A certain portion that is absorbed by the body, which increases its thermal energy. A certain portion that is reflected and transmitted by the body, which has nothing to do with the thermal energy. It does not increase or decrease the thermal energy. I just take it and give it back. It doesn't do anything to me. Just take it and transmit it back. It doesn't do anything to me. Okay? So three portions. G absorbed, I'm going to write this out. G absorbed, there is some G reflected, REF reflected, and then G transmitted through the volume. So G is G absorbed, reflected, transmitted. This is the portion absorbed. This is the only portion of the incident radiation that has anything to do with the thermal energy of the body. So G absorbed increases the thermal energy of the body. The other two are portions that are reflected and then transmitted. Reflected plus transmitted. Please let me know if my writing is not clear. I just lost out a D here, but please let me know. This has nothing to do with the thermal energy of the body. So G absorbed, G reflected. Transmitted does not affect the thermal energy of the body. Of the body. So far, so good? So I have a surface? Yes, this question.
So, when, for G transmitted, where is it going? Like, is it going?
Through the volume.
Oh, it goes through.
Through the volume, right. And we're going to do the following. We're going to say that for most solid bodies, and pretty much all the liquids that we will be studying in this course, we will consider them to be opaque, which means that there is no transmission of the incident radiant flux. Whatever you are sending to the body is either absorbed and a portion of it is reflected. Okay, so I'm going to write out those assumptions here. I want to keep this guy, so do the following. I want to see all the equation. Okay, that's fine. So for us, we will consider the bodies that we study to be opaque bodies. Which essentially tells us that G transmitted is 0. Approximately 0, okay? And so the net G is just the G absorbed and G reflected. If you have gases, for example, they are transparent. Water is semi-transparent. So if I have a semi-transparent surface, it is possible that a certain portion of the incident radiant flux is transmitted through. Or if I have a fully transparent body, then all of the flux will be transmitted. Nothing will be reflected and absorbed. Gases behave that way. Okay? Alright, now we are going to define a new term using whatever we have so far. The net radiant flux from the surface to its surroundings. So net radiant flux from surface to surroundings. I'm going to call this as Q double prime radiation. What do you think this is going to be equal to, looking at the figure that you have here? Remember, if a surface loses radiant energy due to emission, changes its thermal energy. Due to some amount of thermal energy incident, radiation incident on the surface, a portion of this is absorbed, which also changes its thermal energy. The other two components do not affect the thermal energy. So what is the net radiative flux? From the surface to its surroundings. Somebody gives you something, you keep a portion of that and give something back to somebody else. You give something of your own to somebody else as well. What's the net thing that you have? Anybody? Yes, yes.
Is it E minus alpha G?
So it's E is the emitted energy, radiant flux, minus G, just G or G with a subscript on it? Yes.
G absorbed?
G absorbed. You see, the other two components do not change the thermal energy of the body. Does not have anything to do with its internal energy. Okay, so you look at only components that affect the internal energy, so this is going to be E minus G absorbed. These are only the components that affect the internal energy. And we're now going to do the following. We're going to assume that I have a surface that is enclosed by a very large surrounding.
Question.
Yes, question.
What was the G reflection?
Say that again.
The G reflection.
Right, so the G reflection and the G transmitted does not affect the thermal energy of the body. The only components that change its thermal energy will be the absorbed quantity, which will increase its thermal energy, and the emission, which will reduce its thermal energy. So what is the net quantity that changes the thermal energy of the body? It's the emitted minus the absorbed. Okay?
Is that from the surface to the surrounding?
From the surface to the surroundings, absolutely.
Does the G ref get some of it go to the surrounding?
It could, but it's not doing anything to the surface, right? Whatever it does to the surrounding is a surroundings problem. You see, it's not our problem. Whatever is happening on the surface is our problem. This is confusing, certainly confusing, and it's understandable. I am looking only at the surface, not the surrounding. If I look at the surface, there is a certain amount of energy that is sent by the surface of its own accord, which is the amount of energy emitted. Because the surface is surrounded by many things, it will have incident radiant flux on it, but only a portion of this flux is going to change its internal thermal energy. And that's going to be G absorbed. The rest of them, it may affect the surroundings, it might affect the volume through which it might go back into other surroundings, which does not have anything to do with my surface. You see. Okay, so that's important to understand. So this is a surface phenomenon. Very nice. If you have questions, please stop me. Very good of you to point out and ask for clarifications. And now we're going to assume the following. Okay? So assume very large surrounding, very small surface, temperature of the surrounding is T surround. Temperature of the surface is Ts. In this particular situation, G, capital G, is the irradiation from the surrounding to the surface. from the surrounding to the surface. It can be approximated by the Stefan-Boltzmann law. For this particular assumption only, please caveat, very large surrounding, very small surface. So the sun and the earth is really small compared to the size of the sun. So large surroundings, small surface, if that is the situation, the radiant flux that is incident on us is given by Stefan-Boltzmann law, sigma times T surrounding to the power 4. But of all the flux that is incident on us, we are going to take only a portion of it which will increase our thermal energy. So G absorbed is going to be a fraction of the incident radiant flux, and this fraction is called as alpha. Alpha is called the absorptivity of the surface. It's once again a function of the geometry of the surface, it's a function of the texture of the surface, and it's a function of how close the surroundings are to the surface, the distance between the surrounding and the surface. Okay, so it's a quantity that's a function of many different things. We're going to look at it. It's also a spectral quantity, depends on the wavelength, it's a directional quantity, depends on the roughness of the surface, finish of the surface, and so on. For the time being, alpha will be given to you, epsilon will be given to you, and if I now combine everything, I have the following nice equation for radiative heat transfer. And the last assumption before that. So this is assumption 1. Assumption 2. We're going to be working with special surfaces called as gray surfaces. This is our third assumption. And a gray surface is defined as a surface whose emissivity is equal to its absorptivity. Alpha is equal to epsilon. This is the definition of a gray surface. Many quantities can identify themselves as gray surfaces. The sun is an example of a gray surface. Its absorptivity and emissivity are approximately equal over certain ranges of temperature. Depends on the temperature range. For the time being, these will be given to us. We will go into the physics of it, so bear with me. And so from that, G is this equation. G absorbed is alpha times G, which is epsilon times G, because I have a gray surface. So this is sigma epsilon T surrounding to the power 4. Radiant flux emitted by the surface is E, which is epsilon times E suffix B, which is sigma epsilon Ts to the power 4. You see the difference here. Radiant flux that is emitted depends on the temperature of the surface. Radiant flux that is incident on the surface depends on the temperature of the surrounding. In a special situation where we have a gray surface, the details of which have not been explained yet, but hang on to it until we hit radiation. In such a situation, for my surface, epsilon and alpha are the same. And if I now combine everything together, Q double prime, epsilon minus G absorbed, or Q double prime is sigma, is a common factor, epsilon is a common factor, Ts to the power 4, T surrounding to the power 4. Okay, do the substitutions, you'll end up getting these two. Directionality from the surface to the surrounding. which means if I'm looking at from the surrounding to the surface, I just have to invert it back. Okay? Not really interested in that at this point in time because I could have multiple surroundings, not just one enclosure. Okay? Alright. Things to keep in mind: sigma we define, Stefan Boltzmann constant, units for sigma. Epsilon is dimensionless, it's a fraction. Always, in radiation heat transfer, temperature is in Kelvin. Okay, so 3 equations, and I'm going to put up an equation sheet which will contain all these equations that we have. Yes, question?
This is only for gray surfaces, correct?
Absolutely. This is under the caveat. Okay, let me write this down. So this is for large surrounding. Small surface. Gray surface. Which implies that alpha is equal to epsilon. If our surface is not gray, then I will have to give you the absorptivity. Yes, question.
I know it might not be important yet, but how large is large?
That's a good question. So we need to quantify how large is large. For the time being, we will not worry about it. We will just say that assume this to be a large surface and a small as a small surrounding, a small surface, but we will quantify that. Okay? Depends upon how close the surface is. It depends upon the temperature of the surrounding, the wavelength at which the energy is coming into us, and so all of these play a role, and it depends upon how many surfaces are surrounding the actual surface itself. So multiple factors. And when we go into radiation, we will quantify this large surrounding by what is called as a view factor. For many situations, if the view factor is close to a certain number, we say it's a large surface. So as I said, the aim is to introduce you to some equations whose antecedents we will spend time studying. Okay, so for the time being, just go with the flow. The very last thing I want to introduce for the day, and then we'll be ready for problems on Wednesday, is the first law of thermodynamics from the standpoint of heat transfer. It's not as if the first law has changed because you're taking heat transfer. It is just that you're writing it in a different form. The first law is the first law. Energy cannot be created, neither can it be destroyed. It can only be converted from one form to the other. From thermodynamics, you know the following. dECV by dt, Q net minus W net. In thermodynamics, you'd have had a dot on top of these quantities. I'm not going to use it. Okay, these are all in watts. So this is in watts. Okay. Q net, I'm going to write it in the following manner. And so I'm going to consider a control volume. The dashed lines are the control surface for the control volume. It makes a huge difference as to where those lines are drawn, as you know from thermodynamics. We will see those details in the next class. So for the time being, I'm going to assume that there is some heat into the control volume. There is some heat out of the control volume. There is some work done by the control volume on its surroundings. And perhaps you are using a pump and pumping in fluid into the control volume, so there is a certain amount of work input into the control volume. Who knows? Wn. So Q net is the net heat in minus the net heat out. W net is the net work done by the control volume, so this has to be the output work minus the input work. Please notice the differences between the two. Q net is the net input heat transfer. W net is the net output work transfer. ECV is the total stored energy. And so E dot CV is the rate of change of the stored energy. Rate of change of total stored energy this is my workout for the day. I need some, I guess. This E dot CV is split into multiple parts. Once again, good news, right? So E dot CV is split into two parts, E dot stored and then E dot generated.